In example 4, we are asked to evaluate the given integral by first converting to a more appropriate coordinate system. And we can see that the limits and the function are not that user-friendly. So converting to a more appropriate coordinate system is going to make our life when we are integrating a lot easier. Before we decide which coordinate system we are going to go for, we are going to draw the region of integration first that is described by our limits of integration. And like before, in previous sections, we are going to work from the inside out. So let's draw. Here's my coordinate system, x, y, z. And since the innermost limits are limits with respect to y, you can think about it describing a surface on the left and a surface on the right. So for the left surface, we use a lower limit. So we have y is equal to minus the square root of 1 minus x squared. And on the right, we are using the upper limit. We have y is equal to the square root of 1 minus x squared. Okay, let's square both sides. That tells us that y squared is equal to 1 minus x squared. And rearranging that, we see that x squared plus y squared is equal to 1. That's the surface described on the left. On the right, it's very similar. We have also y squared is equal to 1 minus x squared by squaring both sides. And that also gives us x squared plus y squared is equal to 1. Now, what does a surface described by x squared plus y squared equals 1 look like? That is the equation of a cylinder centered at around the z-axis of radius 1. So let's try to draw that. So I have 1 right here, I have 1 right here on the y-axis, and I'm going to draw a circle with that radius in the xy plane. And then I'm going to go up. And so I'm getting a cylinder like that. Now, the only question is which part of that cylinder are we interested in? And that's where the x and the z limits are going to help us. So our x limits are minus 1 is less or equal to x is less or equal to 1. And our z limits (0) is less or equal to z is less or equal to 1. So looking at that, we want x to go all the way from minus 1 to 1. So if I extend the x-axis into the negative direction, I want to go all the way from minus 1, stop doing that, to 1. So I have the entire circle in the xy plane. And z goes from 0 to 1. So I'm getting part of a cylinder from that is bounded below by the xy plane and above by the plane z equals 1. Okay, so now we can describe this region W. So let's describe W in terms of a different coordinate system. And so W is our cylinder, and since this is a cylinder, it makes sense to use cylindrical coordinates. All right, cylindrical coordinates use r, theta, and z. And we have r goes from 0 to 1. Theta, we have complete circular symmetry, so we are going all the way from 0 to 2 pi. And z, as we said, we are starting at z equals 0 and going up to z equals 1. So those are going to be our limits of integration. So let me write down our original integral. We went from 0 to 1, from -1 to 1, and then we had those two square roots, 1 minus x squared, negative, positive, square root of 1 minus x squared. And then we also have that function 1 over the square root of x squared plus y squared, and dy, dx, dz. Now in cylindrical coordinates, we're going to have our three integrals, and we also have to change the function. Now, since x squared plus y squared is equal to r squared, we can describe this function just as 1 over r, since we're taking the square root of r squared. And then our volume element is r dz, d theta, dr. I could have gone in any order here. Limits now. Z goes from 0 to 1, theta goes from 0 to 2 pi, and r goes from 0 to 1 as well. In our integrand right here, r cancels, so we are ending up integrating from 0 to 1, integral 0 to 2 pi, integral 0 to 1, just dz, d theta, dr. And I'm going to do the first integral by finding an antiderivative, and then I hope you're going to see the pattern. When I integrate 1 with respect to z, I just get z, and my limits go from 0 to 1, so this is the innermost integral. Then I still have d theta, dr. And so here you see, when I plug in 1 and 0 into z, I just have 1 minus 0 d theta, dr. Well, that's 1. Now I would integrate with respect to theta. I get the same thing. I have theta, plug in 2 pi and 0, and then I do the same thing with r and plug in 1 and 0. So overall, what we are having here is 1 minus 0, 2 pi minus 0, and 1 minus 0. That is a total of 2 pi. So that is the value of our triple integral, and we got that pretty easily after we converted to cylindrical coordinates.